The term telematics has been used to describe a host of vehicle systems in recent times. Strictly speaking, however, this term only means those systems which transmit, receive, and process radio signals. In this context, the fundamentals of signal path and signal direction will be explained. This information will then be applied to the relevant vehicle systems. Telematics is an artificial word. The term telematics is formed by blending the terms telecommunications and information technology. It refers to all wireless systems which transmit, receive and process information. Radio transmission inside the vehicle concerns the following systems: radio, TV, telephone, CB radio in trucks, BOS communication systems in vehicles operated by German emergency services organizations and authorities, for example, rescue services, and taxi radio systems. Radio transmission is also used in the navigation system, systems which make use of Bluetooth, the radio-controlled central locking function of the drive authorization system, the keyless go functions, and the tire pressure monitor. All communication, in a spoken conversation for example, is based on an exchange of information. In its simplest form, this involves sending and receiving a signal. The signal is transmitted along the signal path. The signal path and signal transmission become more complex if transmission systems, such as the telephone, have to be employed because of the greater distances involved. In the case of a telephone conversation, the acoustic signal is first transformed into an electric signal, which is sent through a cable and then converted back into sound via a speaker for the person listening at the other end. The transmission process for a two-way radio conversation is even more complex. Here, an acoustic signal is transformed into an electric signal, processed in the transmitter and sent out via an aerial. The electromagnetic radio wave is transmitted via a wireless connection, received by an aerial and converted into an electric signal. This electric signal is then processed in the receiver and reproduced through a speaker as a sound wave once again. The following diagram shows a clear technical description and representation of the signal path. The signal is generated at the source and emitted by a transmitter. The signal travels along the transmission route, reaching the receiver, where it is output at the output terminal. Think of a radio receiver in a vehicle and try to construct the path of the radio signal using the basic diagram as a guide. Put the boxes into the correct order and confirm with OK. You have described the path of the radio signal correctly. The source of the radio signal is the broadcasting studio. The acoustic signal registered there is sent out by the radio station's transmitter. The space between the transmitter aerial and the receiver aerial of the vehicle is called the transmission route. The radio set inside the vehicle is the signal receiver, and the speakers serve as the output terminal. That is, they reproduce the electric signal in an audible form. Remember that interference can occur anywhere along the signal transmission path during a radio transmission. Causes of interference can be identified more quickly using the general diagram. A signal path is unidirectional when signals are transmitted in one direction only. A signal path is bidirectional when the signals are transmitted in both directions. With a unidirectional signal path, the transmission terminals can either only send signals or only receive them, whereas with a bidirectional signal path, the participant terminals can both send and receive signals. The radio transmission systems in the vehicle can also be differentiated accordingly. Unidirectional signals include radio transmission via the sound system, TV, and the positioning function of the navigation system. These systems can only receive radio signals but not send them. Bidirectional systems include radio transmission via the telephone, CB radio, taxi radio, Bluetooth, and radio-controlled central locking. These systems both receive and transmit radio signals. Signals can be sent and transmitted either uncoded or in encoded form. Uncoded radio signals can be understood by all suitably equipped receivers. This kind of open transmission is also known as a broadcast transmission. Examples include radio, TV, CB radio, and some GPS satellite data. Encoded radio signals can also be picked up by all suitably equipped receivers, but they can only be output in a comprehensible form by receivers which have the necessary key to the code. Encoding is therefore used whenever a non-public radio transmission is necessary or desirable. This is the case with mobile phones, pay TV, radio-controlled central locking, and Bluetooth devices. Here you can see the signal path of a radio broadcast. Put the elements in the right order along the signal path and confirm with OK. Very good, that's the right order. The signal path begins at the source, runs from the transmitter via the transmission route to the receiver, and ends at the output terminal, where the signal is reproduced. The telematic systems in the vehicle can be classified as unidirectional and bidirectional systems according to the signal direction or directions. The radio, TV, and navigation system can only receive the relevant radio signals. The following systems, on the other hand, can both send and receive radio signals: the telephone, CB radio, taxi radio, Bluetooth, and radio-controlled central locking. The radio signals of the mobile phone, Bluetooth devices, and radio-controlled central locking are encoded, as they are confidential and must not be accessed without authorization. In this chapter you will be given a general picture of the basic properties of wave propagation. The most important of these are frequency and amplitude, as well as wavelength. You will see how radio waves are created, how they travel and carry signals. The section on signal transmission includes a description of modulation and bandwidth. A signal, for instance an acoustic signal, manifests itself as an oscillation. Each oscillation can be represented in terms of its course over time. An oscillation becomes a wave if it is repeated. It reaches its maximum deflection at the vertex. The distance from the neutral line to the vertex is known as the amplitude. In an electric oscillation, like this one, the amplitude is expressed as voltage. The amplitude is a measure of the strength or intensity of an oscillation. The length of each oscillation is known as the oscillation duration. The frequency is the number of oscillations of a wave per second. The unit of measurement of frequency is the hertz. How high is the frequency of the wave shown? Please select the correct solution and confirm with OK. Very good. You have selected the correct frequency. The wave oscillates twice per second. Its frequency is therefore 2 Hz. The frequency can be stated in hertz, kilohertz, megahertz, or gigahertz. The frequency of sound waves is perceived as pitch. The higher a note, the higher its frequency. You can examine the relationship between pitch and frequency by using the controller to alter the pitch. Arrange the frequency ranges in ascending order, from the lowest to the highest. Drag the boxes into the table and then confirm with OK. Yes, that's correct. 1000 Hz is 1 kHz. 1000 kHz is 1 MHz. And 1000 MHz is 1 GHz. Single notes have regular oscillations and do not contain many frequencies. Human speech is less regular and is made up of several frequencies. The oscillations of noises are totally irregular, as a noise consists of a large number of frequencies at the same time. Click on the speaker symbols next to the diagrams to compare the sounds of the various examples.
Computer-based training. Computer-based training. Computer-based training.
How is frequency determined when expressed in hertz? Please select the correct answer and confirm with OK. Yes, that's correct. The frequency of a wave results from the number of its oscillations per second. For example, a sound which oscillates 440 times per second has a frequency of 440 Hz. By contrast to an oscillation, with a wave, a sound or radio wave for example, we study its propagation not only in terms of time, but also in terms of space. This is established by calculating the wavelength. The wavelength is the distance covered by a wave in the course of one oscillation. It is expressed in meters or kilometers, for example. The symbol for wavelength is the Greek letter lambda. To calculate lambda, the propagation speed c and frequency f of the wave must be known. The wavelength lambda is calculated by dividing the speed of propagation by the frequency. The standard pitch A is used to tune musical instruments. Its wavelength can be calculated using the formula mentioned before. The frequency of the standard pitch A is 440 Hz. The wave travels at the speed of sound. The speed of sound is around 300 meters per second in air. Now arrange the figures for frequency and speed correctly in the formula and click on OK to calculate the wavelength. That's correct. To calculate the wavelength, you have to divide the speed of travel by the frequency. That's 300 meters per second divided by 440 Hz. And that leaves you with 0.68 meters. The wavelength of the standard pitch A is therefore 68 centimeters. Just as you can calculate the wavelength of a sound, you can also determine the wavelength of a radio signal, a VHF radio signal, for example. The speed of propagation of radio waves and light in air is about 300,000 kilometers per second. That's the speed of light. Now use the formula from before to calculate the wavelength of a radio signal of a frequency of 100 megahertz. However, before you insert the figures into the formula, you should note that the speed of propagation is given in meters per second, and frequency is stated in hertz. Now arrange the figures correctly in the formula and confirm with OK. Exactly. That's correct. With a propagation speed of 300,000 kilometers per second and a frequency of 100 megahertz, lambda equals 3 meters. The wavelength of this VHF radio signal is thus 3 meters. A radio transmitter generates electric oscillations with the help of an electric oscillating circuit. The electric oscillations are emitted by the transmitter aerial in the form of an electromagnetic wave. Radio transmitters work on precisely defined frequencies. By contrast to these controlled emissions, electromagnetic waves can also be generated spontaneously, by lightning in a storm, for example, or through sparks in electric motors that are not interference suppressed. These kinds of uncontrolled radio waves have an extremely wide range of frequencies and can therefore lead to interference in radio communication. Radio waves travel outwards from the transmitter aerial in all directions. They have a far greater range than sound waves, and can travel through a vacuum, as they are not bound by matter. Radio waves can also be used for transmissions via satellite. In a receiver aerial, the electromagnetic radio waves induce electric oscillations. These are processed by the receiver. The length of an aerial has to be adjusted to the wavelength of the radio wave for which it is to be used. For example, a typical aerial length is a quarter of the wavelength. Shorter aerials can also be used to receive waves. A separate CBT program is available which studies the different aerials used on vehicles. The further a radio wave travels, the more its amplitude decreases, because the wave propagates in all spatial directions. If the distance from the transmitter is doubled, the wave's amplitude decreases to just a quarter of its original value. The wave amplitude created by the transmitter aerial thus determines the range of the radio wave. The greater the amplitude, the further the wave can be transmitted. What properties do radio waves have? Please select the correct statements and then confirm your selection with OK. That's right. Radio waves are not bound by matter. This allows them to travel both in the atmosphere and in a vacuum. Radio waves can also be generated spontaneously, by a lightning strike, for example, and this can cause interference in radio reception. Their amplitude reduces as the wave propagation distance increases. At double the distance, the wave's amplitude decreases to just a quarter of the original value. Radio waves travel at the speed of light. The frequency ranges of radio waves are divided into units of 10, from long waves, whose length is measured in kilometers, to millimeter-length waves. Various frequency bands in the frequency ranges are reserved for the different potential applications of radio transmission, from radio broadcasts to UMTS mobile communications. The use of these bands is regulated by law on a national and international basis through a frequency allocation plan. Move the controller to see the European frequency distribution with relevant examples. In telecommunications, signals such as a telephone conversation, for example, are known as wanted signals. In the case of radio transmission, these are carried by the carrier wave of a transmitter. The carrier wave, which is of a high frequency, is modified according to the wanted signal, which has a low frequency. This process is known as modulation. A modulator is required for modulation. The modulator changes either the amplitude or the frequency, or the phase of the carrier wave according to the information of the wanted signal. The modulated carrier wave of a radio transmitter carries the wanted signal to the receiver. The received high-frequency signal is demodulated. In this way, the low-frequency wanted signal is reconstructed for output. In amplitude modulation, the wanted signal is transferred onto the amplitude of the carrier wave. This means that the amplitude of the carrier wave is modulated in accordance with the wanted signal. In frequency modulation, the wanted signal is transferred onto the frequency of the carrier wave. This means that the frequency of the carrier wave is modulated accordingly. Amplitude and frequency modulation are used in the transmission of analog signals. In the case of phase modulation, alterations in the state of the wanted signal cause a phase shift in the carrier wave. This type of modulation can be used for analog signal transmission, but is used mostly for transmitting digital signals. Interference in radio reception is caused by interfering waves, which mix with the carrier wave in the receiver. Imagine radio reception in a vehicle, for example. This can be impaired by electric motors that are not interference suppressed. Click several times on the electric motor as soon as the transmission of the amplitude-modulated signal begins, in order to see the effects of this kind of reception interference. Click again several times on the electric motor when the transmission of the frequency-modulated signal begins. Amplitude-modulated signals are more susceptible to reception interference than frequency-modulated signals, as the amplitude interference of the carrier wave is transferred to the wanted signal as amplitude interference. By contrast, the wanted signal can be reconstructed virtually perfectly in the demodulation of the FM signal, as the amplitude of the carrier wave is not a factor here. Click on the speakers to hear the effects of the interference sources. The human sense of hearing, for example, can perceive sound in the range from 16 Hz to 20 kHz. Audible sound oscillations can therefore have a bandwidth of approximately 20 kHz. If these oscillations are frequency modulated on a carrier frequency of 100 MHz, the carrier wave requires a total bandwidth of 40 kHz for full transmission, as both difference and added frequencies are generated at the same time through the modulation. The carrier wave then oscillates in the frequency range of 99.98 to 100.02 MHz. If, however, the stereo effect is to be achieved, and in order to transmit other additional control signals, a bandwidth of 150 kHz is required for transmissions from radio stations. In Germany, FM radio stations broadcast between 87.5 and 108 MHz. This means that some 136 FM stations can broadcast their programs within this frequency range. Which properties of the carrier wave have been altered here through the various modulations? Put the boxes in the right order and confirm with OK. Very good. The order is correct. The first diagram shows a phase-modulated carrier wave. The second signal is amplitude-modulated, and the third is frequency-modulated. Radio waves have specific frequencies and the corresponding wavelengths. Frequency is the number of oscillations of the wave per second. It is expressed in hertz, kilohertz, and other multiples. The wavelength is the distance which the radio wave covers during one oscillation. It is expressed in meters or other suitable units of length. For radio transmission, low-frequency wanted signals are modulated on high-frequency carrier waves. In analog transmission, amplitude and frequency modulation are more commonly used. Phase modulation is used primarily for digital signal transmission. As every radio transmission requires a certain bandwidth, the use of the different frequency bands in the various frequency ranges is regulated on a national and international basis by a frequency allocation plan. In this chapter you will see which factors can cause interference in radio transmission and examine in detail the effects of this interference. This chapter will also explain what electromagnetic compatibility is and how it can be ensured. The propagation of radio waves can be altered or impeded. Sometimes they cannot reach an area at all. This phenomenon is known as shadowing. These shadowing zones are created primarily by absorption or reflection. Click here to find out what these two terms mean. Radio waves lose energy if they have to pass through a medium, as the medium absorbs the wave. This means that the medium converts the wave's electromagnetic energy into heat. The radio signal is weakened as a result. For example, the radio reception in front of a building is better than from inside or behind it. Large buildings or hills may even absorb the radio waves entirely, resulting in the shadowing we mentioned earlier. Like all electromagnetic waves, radio waves are reflected by electrically conductive surfaces, which means that the waves are thrown back by such surfaces, which include buildings with metallic facades, machines, and vehicles. Reflected radio waves can also disrupt radio reception, as they arrive at the receiver with a time lag after the directly received radio waves. Radio reception can also be affected by interference inside vehicles. The outer mesh metal shielding of high-frequency cables, in particular, must remain at a precisely fixed distance from the inner conductor, so that the high-frequency signal can be transmitted with as little loss as possible. If the aerial cable becomes pinched or entrapped, for example, there will be interference through voltage drop and through reflection. This cannot be identified as a break or short circuit using a multimeter. Instead, the impairment can only be registered using high-frequency measuring equipment. What does the term shadowing mean? Please select the correct answer and confirm with OK. That's correct. Shadowing occurs when radio waves are so heavily blocked or altered in their travel that they can't reach certain areas. The abbreviation EMC stands for electromagnetic compatibility. This refers to the resistance of electronic vehicle systems to interference from outside factors, and the interference suppression capability of these systems, that is, the ability to avoid causing interference inside the vehicle, as well as their ability to avoid emitting interference from the vehicle. Electromagnetic compatibility is therefore tested in an EMC laboratory, according to legal guidelines, especially with a view to the danger of interference emitted from the vehicle. In practice, the most important cases are those where electromagnetic compatibility is not sufficient, that is, where it is faulty. The control unit of the distance control system, for example, cannot correctly evaluate the signals from its radar sensors if it encounters interference from a powerful external radio transmitter. Where possible, the electronic systems inside a vehicle, in particular control units and radio transmitters, are designed and built with optimum EMC. To this end, the following measures are taken to shield both the systems and cables: insulating and twisting the cables, putting a mesh metal outer shield around the cables, correct cable routing, the adequate design of the control unit housing, the correct use of the mass points specified by design, the use of fiber optic systems, installing interference suppression capacitors or filters. Click on the different means and measures for relevant examples and explanations. Insulated and twisted cables are used in CAN networking, for example. High-frequency cables, in particular aerial cables, are fitted with a metal shielding. Cables susceptible to interference can be laid in separate cable ducts. For the same reason, certain systems, airbags for example, may require their own cable routing. The housing of control units can, for instance, be metallized. The use of predetermined mass points allows controlled mass current flow. Fiber optic systems such as MOST or D2B are impervious to electromagnetic interference, as light does not emit radio waves, nor is it affected by them. Specially designed capacitors and filters prevent electromagnetic interference. What does electromagnetic compatibility involve? Please select the correct statements and then confirm with OK. Perfect. Electromagnetic compatibility covers the resistance of the vehicle's electronic systems to interference caused by outside factors and the interference suppression capability of these systems. That is, the ability to avoid causing interference from the vehicle and to avoid suffering it from outside the vehicle. Interference in radio reception is caused primarily by the absorption and reflection of radio waves. In extreme circumstances, an object can completely shadow the receiver, impeding radio reception. Interference can also be caused by problems with the receiver cables. Electromagnetic compatibility is also a significant factor here. Where possible, control units and radio transmitters are designed and built with optimum EMC, in order to ensure interference-free radio transmission. The chapter on signal processing compares analog and digital signals and describes the process of digitalization. You will then be given an explanation of data compression and multiplex transmission. Many signals sent by radio transmission, such as radio station broadcasts, are analog signals. These analog signals are recorded beforehand as unbroken and continuous electric oscillations using a microphone. A digital electronic data processing signal is characterized by the phased transition between 0 and 1. In a diagram, this would be shown as a rectangular curve, the amplitude of which can take on two different values, that is, one for the state 0 and another for the state 1. Therefore, a distinguishing feature of a digital signal is its stepped form. Digital signals have the advantage over analog signals that they can be transmitted and processed with no interference or loss of strength. The conversion of an analog signal into a digital signal involves sampling and measuring the analog oscillation at set intervals. The number of amplitude values measured and transmitted per second is known as the sampling frequency or sampling rate. The higher the sampling frequency, the more precisely the analog signal can be digitalized. Digitalization is carried out by an analog-digital converter. This device reproduces the sampling process as binary numbers, that is, as combinations of the numbers 0 and 1. Now simulate the digitalization of this analog signal by slowly dragging the sampler and analog-digital converter to the right. You have used digitalization to transform an analog oscillation into a rectangular oscillation. This can be transmitted by radio through phase modulation. Examples of digital radio transmission are digital radio, digital television, and mobile communications. What are the distinguishing features of digital and analog signals? Put the boxes in the correct order and confirm with OK. That's right. The stepped rectangular oscillation of digital signals is created by the phased sequence of its two voltages. By contrast, analog signals have an unbroken, continuous voltage. Digitalization increases the signal's data capacity. This can, however, be reduced significantly in order to make processing and transmission more practical. This is done using various compression processes. Image data, for example, is compressed by means of the JPEG process, while audio data compression uses the MP2 or MP3 process. Whatever the specific process involved, all types of data compression condense similar or identical information, allowing the overall quantity of data to be reduced. JPEG compression mainly reduces the quantity of color information, Digitalization starts by storing the color data for each individual pixel. The compression process condenses identical color values of different pixels and stores them once only. The higher the compression factor selected, the more similar color values are interpreted as being the same and condensed. The quantity of data is therefore lower, but the image quality is reduced accordingly. Click on the two more highly compressed photos to see the results of various degrees of compression more clearly. The multiplex process is used primarily for digital radio transmissions in order to transmit several signals using only one transmitter. The signals are switched over to the carrier wave sequentially by a multiplexer. Only a fraction of the transmission time, the time slot, is available for each individual signal. However, this time slot is sufficient to transmit all the data sent using the multiplex method, as the size of the signal data has been reduced significantly through the compression process. In the receiver, the demultiplexer registers only the wanted signals from all those transmitted. Click on the speakers to select these signals.
Waves are lapping calmly, steadily against the shore. A light, warm breeze is blowing. The air tastes faintly of salt. The sun feels pleasantly warm.
Traffic report. No delays on the freeways reported.
Digital signals have the advantage over analog signals that they can be transmitted and processed with no interference or loss of strength. The digitalization process deals with enormous quantities of data. These are then reduced in size through compression to the point where effective transmission techniques, such as the multiplex process, can be used. You come now to the test section of this CBT program. You can either select test exercises from this page, or you can simply click on Next to proceed to the next exercise that has not yet been completed. How are the stations of a radio broadcast arranged from the source to the output terminal? Drag the boxes into the table and confirm with OK. How is frequency determined so that it can be expressed in hertz? Please select the correct answer and confirm with OK. Which symbol stands for which physical dimension? Match the dimensions with the symbols and then confirm with OK. How does a radio transmitter work? Arrange the steps in the correct order and confirm with OK. Which radio signal can be altered by interfering waves to the point where interference also affects reception? Please select the relevant signal and confirm with OK. How large is the bandwidth of audible sound waves? Click on the correct solution and then on OK. What factors can impair analog radio transmission inside a vehicle? Please select the correct solutions and confirm with OK. What does the abbreviation EMC stand for? Click on the correct solution, then on OK. What are the advantages of digital signals over analog signals? Click on the correct boxes, then on OK. You have now completed the test. Here is your test result. If you would like to read through any of the exercises again, just click on the exercise's name. You can also click on the cross-references to the content section if you would like to review the relevant topic.